Yes, it is possible to limit the extent of a Zone 1/2 within an ink cartridge filling cabinet to a negligible extent through the use of forced extraction. This can be achieved by implementing a robust mechanical ventilation system that meets certain criteria. The ventilation system should provide sufficient air changes per hour to maintain a safe atmosphere within the cabinet. The air changes per hour will depend on the size of the cabinet, the type of solvent used, and the leak rate. A minimum of 6 air changes per hour is typically recommended for Zone 1 areas. The extraction system should create an air velocity at the point of the potential leak that prevents the formation of a flammable atmosphere. It is recommended to maintain an extraction velocity of at least 0.5 meters per second. The ventilation system should capture the extracted air and discharge it safely outside the building. The discharge point should be away from any potential ignition sources. The ventilation system should be equipped with monitors to ensure proper operation and alert personnel in the event of any malfunctions. If the ventilation system meets the above criteria, it is possible to create a dilution zone within the cabinet. By continuously diluting the solvent vapors with fresh air, the concentration of flammable vapors can be kept below the lower explosive limit of the solvent. If the ventilation system is not able to effectively maintain a non-hazardous atmosphere within the cabinet, then ATIC-certified electrical equipment will be required. ATIC's equipment is designed to be safe for use in potentially explosive atmospheres. It is theoretically possible to limit the extent of a Zone 1/2 within an ink cartridge filling cabinet to a negligible extent through the use of forced extraction. However, a comprehensive risk assessment and detailed design of the ventilation system are essential to ensure the safety of personnel and equipment. It is recommended to consult with a qualified ventilation engineer to determine the appropriate ventilation system for your specific application. The key here is understanding the relationship between air changes per hour, extraction velocity, and maintaining a safe atmosphere. The ventilation system acts as a primary safety control, diluting the concentration of potentially flammable vapors. Think of it like this: a small leak in a large room might not be hazardous, but the same leak in a confined space could quickly create a dangerous situation. The forced extraction system is essentially enlarging the effective volume of the space, continuously removing the solvent vapors and preventing them from accumulating to a dangerous level. Air changes per hour, or H, is a measure of how many times the air volume within the cabinet is completely replaced in 1 hour. A higher ACH means that the air is being replaced more frequently, which is more effective at diluting and removing solvent vapors. The specific ACH required will depend on several factors, including the size of the cabinet and the volatility of the solvent being used. Extraction velocity refers to the speed at which air is being drawn into the extraction system. This velocity is crucial for capturing the solvent vapors at the source of the leak. If the extraction velocity is too low, the vapors may escape and create a flammable atmosphere. A minimum extraction velocity of 0.5 meters per second is generally recommended, but this may need to be increased depending on the specific application. Monitoring the ventilation system is essential to ensure that it is operating correctly. This may involve monitoring the airflow rate, the extraction velocity, and the concentration of solvent vapors in the exhaust air. If any malfunctions are detected, the system should be shut down immediately and the problem should be addressed. It is very important to properly select the components of your mechanical ventilation system, such as the materials for the ductwork, blower, and filters, to ensure that it can withstand the effects of the solvents. If a non-hazardous atmosphere cannot be guaranteed by the exhaust ventilation system, then the installation of ATIC-certified electrical equipment is necessary for any equipment that will be installed in a Zone 1/2 environment. ATIC's equipment refers to equipment that has been specifically designed and tested to be safe for use in potentially explosive atmospheres. This equipment is designed to prevent explosions from occurring, even in the presence of flammable gases or vapors. The forced extraction system needs to be designed and maintained properly to ensure that the system is functioning properly. This may require regular inspections, maintenance, and testing. It is important to keep records of all maintenance and testing activities. A comprehensive risk assessment should be conducted to identify all potential hazards associated with the ink cartridge filling process. This assessment should take into account the type of solvent being used, the potential leak rates, and the ventilation system's effectiveness. The results of the risk assessment should be used to determine the appropriate safety measures. If the ventilation system fails or is not properly maintained, a potentially explosive atmosphere could develop within the cabinet. This could lead to a fire or explosion, which could cause serious injuries or fatalities. It is important to take all necessary precautions to prevent this from happening. Proper grounding and bonding can help to prevent static electricity from building up, which could ignite flammable vapors. All electrical equipment within the cabinet should be properly grounded and bonded to prevent static electricity from accumulating. The ventilation system should be designed to minimize the risk of sparks or other ignition sources. All electrical equipment within the cabinet should be installed and maintained in accordance with the applicable electrical codes. The forced ventilation should also be rated for the environment they are installed in. Be aware of the possible types of protection methods that are available for different electrical equipment, such as explosion-proof, intrinsic safety, purged and pressurized, increased safety, non-incentive, and oil immersion. In order to limit the extent of Zone 1/2, 1. Determine the properties of the solvent used, including its lower explosive limit, upper explosive limit, flash point, and auto-ignition temperature. This information is critical for understanding the potential hazards associated with the solvent and for designing an effective ventilation system. 2. Calculate the required air change rate based on the volume of the cabinet, the solvent evaporation rate, and the desired safety factor. This calculation will determine the amount of air that needs to be exhausted from the cabinet to maintain a safe atmosphere. 3. Select an appropriate extraction fan that can provide the required air change rate and static pressure. The fan should be sized to overcome the resistance of the ductwork and filters. 4. Design the ductwork to ensure efficient airflow and minimize pressure drop. The ductwork should be made of materials that are compatible with the solvent being used. 5. Install a filter system to remove solvent vapors from the exhaust air. The filter system should be designed to effectively capture the solvent vapors and prevent them from being released into the environment. 6. Install a monitoring system to continuously monitor the airflow rate, solvent concentration, and other critical parameters. This system will provide early warning of any potential problems with the ventilation system. 7. Develop a written procedure for operating and maintaining the ventilation system. This procedure should include instructions for starting up, shutting down, inspecting, and troubleshooting the system. 8. Train personnel on the proper operation and maintenance of the ventilation system. Personnel should be able to identify potential problems and take corrective action. 9. Conduct regular inspections and maintenance to ensure that the ventilation system is operating correctly. This should include inspecting the fan, ductwork, filters, and monitoring system. 10. Review and update the risk assessment and ventilation system design periodically. This will ensure that the system remains effective and that any changes in the process or environment are taken into account. Remember that the goal of forced extraction is not simply to remove solvent vapors but to dilute them to a concentration below the lower explosive limit. The lower explosive limit, OLL, is the lowest concentration of a flammable gas or vapor in the air that will ignite. By maintaining the concentration of solvent vapors below the LEL, the risk of a fire or explosion is significantly reduced. The location of the extraction points is critical. They should be placed as close as possible to the potential leak sources to maximize capture efficiency. Consider using multiple extraction points to ensure that all areas of the cabinet are adequately ventilated. The design of the cabinet itself can also play a role in the effectiveness of the ventilation system. A well-designed cabinet should minimize the formation of dead zones where solvent vapors can accumulate. The cabinet should also be constructed of materials that are compatible with the solvent being used. It is also very important to make sure that the exhaust air is discharged to a safe location where it will not pose a hazard to people or the environment. The exhaust air should be discharged away from any potential ignition sources and away from any areas where people may be present. The ventilation system should be interlocked with the filling equipment to automatically shut down the equipment in the event of a ventilation system failure. This will prevent the release of solvent vapors into the atmosphere if the ventilation system is not working properly. In order to achieve optimal results, it is highly suggested that computational fluid dynamics, or CFD, modeling can be used to simulate the airflow patterns within the cabinet and to optimize the placement of the extraction points. CFD modeling can also be used to evaluate the effectiveness of different ventilation system designs.